All right, good morning, everyone. I'll go ahead and apologize in advance. Losing my voice. We had a music festival here this weekend, and I'm singing a little too hard. So anyway, we're moving on to Chapter 5, where we talk about soils. Of course, a huge factor in crop growth, and we'll have a little take-home lab associated with this chapter as well. I did want to request that people please put up your whatever crop you're going to do for your project on that discussion board. You'll have to scroll down to the bottom for that crop project module. Just get on that discussion board and please put what crop you would like to do. So we've had very few people actually sign up for that. Yes, did anybody?
I'm sorry, I was sick in the hospital, so I missed 2 quizzes. Could you open those up and I can do those?
Yeah, I can open them up to you. I'll try to do that this afternoon for you there, Tyler. Sorry about that, and sorry about your issues there. But yeah, if you just scroll down to the bottom, just pick a crop. Scroll down to the bottom of the module list, and the crop project module is there. Should explain it for you pretty well. And just let me know if you have any questions or concerns, as usual. All right. Well, get started here on Chapter 5, talking about soils, where we get water, where we get nutrients, where we get the anchoring of roots for plants. So soil is incredibly important for crop growth. Everybody see the screen there?
Yep.
All right. Well, so as we all know, soil is an extremely important part of the living world, and actually really regulates a whole lot of different processes. And we look at soil as the product of interactions of 4 factors. First, the parent material. The parent material is what type of rock that the soil was actually created from. And this is a big thing about soil, is that when we're talking about actual soil, it comes from rock. When we grow plants in like a greenhouse or in a potted container, we're not really growing them in soil. We're growing them in what we call substrate or soil media. And it's a mix. It emulates soil, but it doesn't come from rock. It might have some components that came from rock, like vermiculite or perlite, but generally, we're talking about soil coming from actual rock. So that's the parent material part. Next, we have the climate. So in different areas, different soils are created based on what that climate is. More rainfall is going to mean more weathering, more temperature. Higher temperature in tropical areas is going to be more weathering, which will accelerate soil creation processes, but also change the way that soil is created. We also look at topography. The lay of the land itself affects what type of soil you will have. And then the biology. And in the book, they kind of talk about the soil organisms, which is very important. But really, there's all kinds of other plants and animals that deal with the creation of soil from that parent material. So we look at plant roots actually growing into the rock and helping to break it up and weather it. We also look at animals burrowing into the soil, kind of physically mixing rock and different soil types, as well as the soil organisms themselves. So plants, we think of as living above ground, but they also have almost as much mass of the plant underground as they do above ground. And in some cases, they may have more, especially in really dry climates. So what is soil anyway? There are lots of different ways to look at soil and from different perspectives, of course. An engineer, for instance, has a totally different perspective of soil, more looking at how do I get it stable so I can build something on it. Whereas for us, being crop producers, we're looking at soil as how can I get it to actually, produce optimally the crop that I, am trying to get it to produce. So we look at soils as consisting first of the solid fraction in any perspective, which is that parent material, the rock fragments, the mineral portion of it, along with a smaller portion that is the organic fraction, which we look as organic matter as being things that just came from life, basically, from a product of anything that was once living, whether that is plant residues, the above ground or below ground parts of the plant, soil microbes, soil animals, other animals, all of that can eventually become part of the soil, and it becomes the organic fraction. So if we're looking at soil as a pie, right, on a pie chart, the solid fraction and the organic fraction there together account for about half of what we look at as soil. And in that pie, really, about 45% of that half would be just the mineral fraction. And only about 5% of that is the organic matter. Organic matter fluctuates. The mineral fraction doesn't really fluctuate that much unless you're adding minerals to it. And then we look at the liquid fraction. So on the other half of the pie, it's going to be quarter air, or half of that pie is air, half of it is water. So the liquid fraction is water, but also the minerals that are dissolved in the water, which we refer to as the soil solution. And then we also have air in the soil, pockets of air. And in an ideal, production setting, again, these fluctuate. The amount of water and air is going to fluctuate with, seasonal rainfall, with irrigation. But ideally, when plants are being grown, crops are being grown, we look at that as being about half air and half water to get the best growth, optimal growth for plants. Of course, the kind of soil and the ability to support plant growth are influenced by the relative amounts of each component. It's really the solid fraction, the mineral fraction, though, that we can't really influence that much. We can make amendments to it, but really it's coming from what the rock was there in the first place. So it is complex. It is a dynamic system. There's all kinds of different interacting factors and components that are affecting and affected by plants. But to what degree can we change it? And really that's where we're talking about trying to find a place to grow crops. You really want to study up on your soils to see what the soil is, actually capable of growing well anyway. So between the soil solids, we have pore spaces, and they, of course, vary in size. And, a natural soil we think of as being half solids, half pore space. And as I mentioned just a minute ago, that solid phase might be 40 or 45% mineral, only 10% tops of organic material. And then the pore space is either going to be filled with water or air. And that ratio is going to depend on whether there's been rainfall or whether we've watered crops. So again, the most productive soil, we're looking at 50% pore spaces that would be holding air and water. And ideally, we want a good mix of large pores and small pores. We call them macro pores and micro pores. Generally, the macro pores are better at holding air and draining that water out, whereas the micro pores are holding water more long term. So when we think about adding water to the soil, whether we're just looking at natural rainfall or we're just looking at irrigation, whenever water infiltrates into the soil, it begins to fill up these pockets of air first and then move into those micropores. And we have gravity, of course, pulling it down. However, it's not just being pulled directly down through capillary action. And think of that kind of as this network of these pores connected, kind of like your capillaries in your own body. As the water is being drained and moved through that by gravity, it's moving horizontally, vertically, sometimes, up as well through capillary action across this wetting front, moving from dry areas of soil from wet areas of soil to dry areas of soil, from areas of higher pressure to lower pressure. So the water that is left after that gravity has drained all of that easily drainable water out, we call that the field capacity of the soil. And that's where we get to water that is actually available to plants. Let's talk about the parent materials just for a second. So what kind of rock do you have there? Generally in our area, we have a lot of sedimentary rock. That's kind of most of, our region is underlain by sedimentary bedrock. And it's either sandstone or limestone in many cases. We have some spots where we have some schist and shale. And it's that rock that, as it is weathered and broken down, becomes the soil. So we have limestone rock, we're going to have limestone soils. So when we're looking at the parent rocks, we think of just the general type of, the geology of them. So first look at the igneous rocks that are formed basically from volcanic action, from molten rock, magma. So they are composed of minerals such as quartz and feldspar. We can look at sedimentary rocks, which are kind of glued together, right? They're fragments of rock that have been transported and deposited by wind, water, or in some cases, glaciers. So we have like limestone, sandstone, and shale being examples of sedimentary rock. Kind of glued together, cemented together throughout time. And then we have metamorphic rocks that form either from igneous or sedimentary rocks initially, but then are subjected to very high temperatures and pressures to change their structure and composition. So slate, gneiss, schist, and marble are all metamorphic rocks. And usually they were kind of subducted through continental plates and shifted and taken below ground, where they were subject to all this pressure and temperature before they were uplifted and altered. So those rocks together, the different rock types are going to lead to different types of soils. And resulting in, from all these different processes together, the formation of the soil and the accumulation and then subsequently the transformation of the parent material. So it's going to accumulate by the breakdown of these rocks by weathering, and then it's going to form into these unconsolidated layers that are called horizons. And a horizon is just a distinct layer of soil with some differences. Altogether, these layers, these horizons, as they become more and more distinguishable between layers, they develop into what we call the soil profile, which is just kind of like this cross section of the soil, vertically looking at it. So say we get a backhoe, we dig down, or an excavator, we look at that soil profile, we're going to see these different horizons, these different layers, like lasagna. So it's physical weathering is a big part in breaking down that parent material into these horizons over time. So we look at that as a whole lot of different things that can cause the physical weathering. Can be just through temperature changes. So we got water in rocks, we have freezing and thawing that will cause contraction and expansion, that will cause breaking of the rocks, cracking and peeling of it, which we call exfoliation. And that's actually similar to the action of glaciers, although it's over long periods of time. Whereas glacial weathering, which we call glacial till, generally happens a little bit more quickly as these glaciers are moving. And glacial till can move rocks and, break up rocks from, small fractions, small little particles of rock all the way to the size of boulders. And then, they're operating kind of like a plow, which is why we call it this glacial till, and they're pushing them underground and depositing them beneath, beside, or at the end of a melting glacier. So we also have physical weathering that is just a product of just the movement of water, which is also similar to glacier movement, not able to do as much at one time. But we have different types of erosion from moving water. Stream erosion, which is like what we see here, where basically we're getting water concentrated into a particular area. In this case, it's where it's draining off of these agricultural fields. It's being channeled into this area. All that energy is concentrated, and it's causing really strong, hard stream erosion here. We also have sheet erosion, which is after the soil is saturated, when it starts to just run off. The soil can no longer hold water, so it's running off as an entire sheet. That can move a lot of soil too. Rill erosion is kind of smaller channels. And then wave action is also kind of happening from really large events of heavy rainfall. So when we're looking here at this particular area, this is bad, right? We think of this erosion as pretty much being very difficult. I mean, we can't really reclaim it at this point. If we fill it back in with soil, that's not really going to, alter it. We can't really repair it as much. We could grow plants on it and get it to stabilize, but it's really difficult to actually put the soil back once it's eroded. We also look at chemical weathering, and basically we're looking at 4 different processes in chemical weathering of soils. First, dissolution, which is basically where parts of that parent material are dissolving. And this is usually naturally occurring through rainwater, which is slightly acidic. Naturally, just has some more hydrogen ions in there, making it a little bit more acidic and causing it to leach away, picking up some of the actual molecules in the rock and replacing it with other molecules through this chemical process of dissolution. We also have hydration, where we're actually adding H2O, molecular water, to some other compound to form a hydrated material, which then becomes more vulnerable to weathering, basically. We have hydrolysis, which is the reaction between any compound and water to form a more soluble product. And then oxidation, which is basically just reactions from the oxides of the parent material with oxygen. So think of that like rust, for instance, and we see that a lot in soil and in oxidation. If you have iron and it's oxidized, then you have iron oxide. Iron oxide actually is just rust, and it gives it that kind of orange color to the soil. Not all orange soil, though, means that it's high in iron necessarily. So climate has a big effect on the type of soils that are produced. How? Well, first, we think of the high rainfall. We have lots of water, and the soils are going to be more highly leached, taking those nutrients, that mineral composition out of the soil, and it's going to increase the chemical reactions as well. So in areas of high rainfall, we have chemical weathering proceeding at a higher rate, especially if it is coupled with high temperature. So in these areas, generally soil fertility is low because many of the plant nutrients are being leached from the root zone. Typically say that the older a soil is, the more highly weathered it is, and the less plant nutrition it has in it. In arid climates, though, the soils are not highly leached. So we kind of have the opposite effect there. We have calcium and magnesium carbonates accumulating, which causes chemical weathering to proceed at a much slower rate. So where we have high leaching and high rainfall, we have low leaching and low rainfall, makes sense, right? But that often causes an excessive quantity of these salts to accumulate. And that's going to cause these soils to be less productive until those salts can be reduced. All right, so let's look about the whole living aspect of the soil, biology. So we say that up to 50% of the plant's dry matter is in the root system. Generally, it's lower than that, and in some cases it can be higher, especially in arid areas where the plants are, putting much more energy into root growth, or with tuberous rooted plants. What do the roots do? Well, they're supporting and anchoring the plant itself. They're also there to absorb water and nutrients, as we know. And in some cases, especially with tuberous roots, they're providing some storage for food reserves. We have these root hairs that are behind the root tip, and they're actually absorbing the material from the soil as the root tip itself is growing, expanding, and moving into the soil, and in some cases breaking up parts of parent material, looking for these fresh supplies of water and nutrients for future growth. The roots are also actually contributing somewhat to chemical weathering because they can go through this process known as allelopathy, where they're actually secreting and leaching chemicals into the soil to help the absorption of the nutrients, but also contributing to that weathering as well. And just through a regular growing season, old roots are going to die off and are going to be replaced. And more than half of that root system will actually be turned over in just 1 year if we're looking at an annual or a perennial. Roots die, become part of that organic portion of the soil. So we think of the soils as being a home to basically all 5 kingdoms of life: the plant kingdom, the animal kingdom, the fungal kingdom, the protists, and the moneras, the bacteria, and other simple organisms. And these organisms are all contributing in different ways to kind of a below ground soil ecology, which has very profound effects on the soil chemistry, structure, and the function of the soil itself. They actually say that there can be over 1 billion organisms in 1 teaspoon of soil. It's kind of crazy to think about. That's a lot. Bacteria are by far the most abundant of these soil organisms. And there are good bacteria and there are bad bacteria. Some of them can be parasites of plants and other soil organisms. Many of them are involved in the decomposition and the recycling of nutrients. So that below ground pool of nutrients and moving those nutrients. We can also have fungi, of course, which again can be beneficial, can be detrimental too. They can be plant parasites, but most of them are also aiding in that decomposition and recycling. This loop of this cycle of nutrients moving through the soil and into the plants. Also, we talked about this, talking about the ecology. Most of our wild plants are actually associated with some sort of mycorrhiza, some sort of fungal associate that helps them to take up nutrients and water from the soil. So these are plant partners as well. We also have the protists, which can include algae in the soil at the soil surface, are actually able to carry out some photosynthesis and create some food. We also have protozoa that are predators of soil bacteria. Could be of good bacteria or bad bacteria. So again, none of these are microorganisms. We're thinking of all these basically being the microorganisms, and none of them are wholly good or wholly bad. When we get to the macroorganisms, the animal parts, we're thinking of things that in some cases could be microscopic, like nematodes, kind of like worm-like creatures that are a little bit smaller, and again, can be good or bad, can be plant feeders or can be predators of organisms in the soil. We have mollusks, of course, snails, slugs living in the soil. We have annelids, worms, arthropods, lots of different types of insects. We even have crustaceans that live in the soil as well. Those roly-polies, yeah, seen those, right? They're everywhere. Those are actually crustaceans. You know that? Interesting fact of the day. We have all kinds of soil animals, living down there, a whole other food web, really. So there's this ecological thing going on in the soil as well. We have our non-living organic components of soils, and those are, once were living, they're residues of the plants and animals. We have the climate of the area determining what biology is there, how much of the biomass is produced, which also influences how the soil is formed. And we also have that vegetation, the plant life aiding in the soil formation, not just supplying some organic matter through the dying and decomposing parts of the plants, but also by their roots growing in there, actually physically weathering as well. We're talking about organic matter, the OM, the ohm of the soil. It is influenced by the difference of the rates of accumulation and decomposition of the organic material in the soil. Where we have really high decomposition rates, the organic fraction accumulates very slowly. So we're talking about in tropical climates, rainforests, as the soil is not being very productive. That's because there's really high decomposition rates. So they don't really have much organic matter in the soil. Even though there's all kinds of organic matter, all kinds of biomass being produced, it's all caught up in that food web, both above ground and below ground. And very little of it is actually available to the soil or to plants. And in cooler areas, though, where we might have more anaerobic conditions, which is just decomposition occurring without oxygen, it's slower, and organic matter then accumulates much faster. But because of the, just temperature, there's not as much biomass being produced, and that organic matter is not quite as available to the plants. So the type of the root system produced by the plant species, of course, also influences the soil formation. On the topography front, We basically just look at this as, the slope. The steeper the slope is, the more likely it is to, be subject to weathering, erosion as water is flowing downhill, and little percolation actually into the soil. So we have more shallow soils on steeper slopes. And if we have vegetation removed, then we can have really deep gullies cutting into, in some cases, even gently sloping land. And really, the best thing you can do to prevent erosion is just to keep soil covered. That doesn't necessarily need to be through plants. It could be through a mulch, for instance. But, what we see here in this image, we're starting to see some of that rill erosion, which if it's channeled, it could become stream erosion or sheet erosion too. Actually, we see the rill erosion forming here, and then at the bottom, it's starting to form more into some sheet erosion taking place, removing that topsoil, which can expose the parent material, accelerating the weathering, and leading to more rapid soil formation at the bottom of the slopes. So generally, at more gentle land or at the bottom of a slope, we have greater accumulation of soil, especially topsoil. That doesn't mean that it's not subject to erosion, though. If it's on flat land, especially subjected to wind erosion, pulling away particles of soil, it's actually similar to water erosion. High altitudes, higher elevations, we're looking at lower soil and air temperatures, which in turn influence the amount and type of vegetation that grows there. So an increase in elevation, we have a difference in vegetation, which influences that characteristic of the soil. So when we look at, in this image, we're looking at high elevation where we actually have tree line. So above a certain altitude, depending on what your latitude is, trees will not grow. That lack of vegetation is going to cause there to be, less developed soils, basically, and better developed soils at the lower elevations. So what we see on tops of mountains often, really rocky soils. Time is all of these different soil formation factors that we've been talking about, basically just interacting together over time. So the harder the rock is to decompose, the longer it takes for it to decompose. So the younger a soil is, and really this isn't necessarily, again, a good thing or a bad thing. It just means that it's often less developed horizons. So softer rocks, on the other hand, like limestone, require a lot less time, weather very quickly, and can develop into well-developed horizons very quickly. So when we have less developed soil horizons, we think of them as young soils. Even though, the rock itself, the parent material, could be very old, if the horizonation is not very well developed, we refer to it as a young soil. And we're looking at that as the pedology of it. So more on that in a moment, but the soil ped is like the lowest classification of the soil, the most specific. It's like the species of the plant in a way. So as soils develop, the mature soils differentiate into these horizons. We look at these horizons as being three principal horizons. We have the surface layer, the A horizon, which is going to vary in depth, especially if we have, lots and lots of organic matter. We generally have deeper A horizons. Alluvial soils, those that are, developed by the deposition of, nutrients from water and material from water, those tend to have very thick A horizons. A is what we call the topsoil. It's the most important for the production of crops. And most of our crops are generally, their root zone is mostly confined to this A layer. It tends to be darker because it has more organic matter than any of the other layers of soil. Because of that, it tends to be more permeable as well. The higher the organic matter content, the better the water, first infiltration and then movement of water in the soil. So it's also generally the highest level of biological activity occurring there in the soil profile, there in the A horizon. The B horizon is what we kind of think of as the zone of accumulation. This is where we start calling it subsoil. We have all these different nutrients and also textural, structural components moving from the upper layer, the A horizon, down into the B horizon. So generally, we're going to see a lighter color in the B horizon. There's going to be less organic matter and less life there. But we do still have plant growth. We have root growth into the B horizons. Not nearly as much as we have in the A horizons, but some deeper rooted annuals will grow there for sure. Mostly biennials and perennials that we're looking at growing into the B horizon. It's lighter in color, generally a little bit rockier, a little bit more like the C layer. So getting to the C horizon, we have unweathered material. It's most like the parent material. It is the material from which the A and B horizons are formed. That's going to be most like the bedrock. It is also a zone of accumulation as well. We do have the downward transportation of nutrients and some textural components here as well. It's not extremely important for the production of crops in general because we don't have much root growth down there. Doesn't mean that we don't have any. We can have some. And it can be important because it can be, a place where we have things like hard pans that store water. It's an important horizon, even though we don't think of crops really growing very much into it. All right, let's look at soil texture. So the texture is basically just looking at the structure of the soil itself. And we're talking about the structure as the percentage of the different particles in the soil. And it's all determined by the size of these particles. So we look at them as from the largest particles, which we think of as being, visible to the naked eye. Things like big chunks of that parent material, gravel and stone. These we're thinking of, being inches in size, large chunks. We don't really factor those into the soil texture as much, though. We're looking at sand as being the first textural component of soil. It is the largest particle size, and sand particles can vary from, being, in the visible spectrum of the naked eye to being small enough to where you need to look at them through a microscope. So between 2 millimeters in size down to 5/100ths of a millimeter. Between 5/100ths of a millimeter and 2/1000ths of a millimeter, we have silt. And those particles are only visible under a microscope. The smallest particle are the clay particles, and they are below 2/1000ths of a millimeter in size. And they get to the point where you can only see them with an electron microscope. So to actually measure the soil texture, we're going to look at these soil particles and their respective sizes, basically try to calculate their percentages, and then use those percentages to determine what this actual texture of the soil is. And the USDA created this nifty soil texture triangle that is how they classify soil texture. So we have these, first looking at the percentage of sand and silt and then clay to determine where it falls. And for the most productive agricultural soils, we think of as being loamy soils, kind of here in the lower center, where we have more of an even mix of sand, silt, and clay. The higher we get in the percentage of clay, the more clay the soil becomes, right? So this is basically just saying, what are the textural components of the soil and how does that work to create the different factors that lead to crop productivity. So here's just a table looking at how that texture influences soil properties in relation to how we're actually producing our crops. So we're looking at aeration initially. So aeration being the larger pores, basically, of soil. So sand, having larger particles, is going to have really good aeration. And that can be good, right? But it can also be bad because the larger the macropores, the more quickly water is drained through them. We look at cation exchange, and we'll talk about this more on Wednesday. But cation exchange basically is just how nutrients are able to move, throughout soil. It's going to be low in sandy soils. Drainage is going to be excellent. They're going to be highly erodible in more sandy soils because the particles are larger. Temperature-wise, they're going to warm up quicker, especially in the spring, and cool off quicker in the fall. Which, happy first day of fall, guys! It's today is the equinox, right? So we're moving into autumn. Anyway, tillage, very easy in sandy soils. Water holding capacity, though, is low. On the other end of the spectrum, we have the very fine particles, the smallest particles. We have the clay. It's very poor in aeration. It has a high cation exchange capacity. It doesn't drain very well because it's got lots of micropores holding on to a lot of water. It's more difficult to erode. Doesn't mean it's impossible. Definitely still erodes, but it's more difficult. It is very slowly permeable. It warms slowly, mostly because water has a very high specific heat and it holds water longer. So it warms up warms up slower and cools off slower as well. It's difficult to till clay soils, and it has very high water holding capacity, right? So, on the opposite ends of the spectrum of the textural classes, we have good and bad aspects of both of them. So that silt loam, that kind of center, it's the balancing point. That's what we want, right? We do want some clay. We want some sand. We want some silt. We want all three of them in a good productive soil to have the greatest compromise of all of these characteristics in the textural class. And I think this is a good stopping point. So I'll basically just go ahead and ask you guys if you have any questions about what we've discussed so far. It's kind of just the simple parts of soil.
Yeah, I have one question. When you do a soil sample, you're really only covering the A zone. Is that correct?
Say that again. You're only covering the what?
When you're doing a soil sample, you're only covering zone A.
Right. Oh, yeah. Because most of the time you're really just probing zone A and getting, that horizon for what you're setting off. And for most crops, that's all you need to look at too. But in your case, if you're looking at forage grasses, or legumes too. I mean, they're deeper rooted. So you might actually want to try to get some of the subsoil too, looking at the B horizon as well. For most of Virginia, and I'd say most of the arable land in Virginia, the A horizon we're looking at as being, 6 to 12 inches deep, usually, sometimes thinner than that. So if you are growing more deep-rooted crops, then you probably do want to try to dig a little deeper than that. And in our lab, we'll do all kinds of different soil testing. Whenever you're actually doing soil sampling and sending them off to a lab, what they report back to you, we're not actually looking at the texture of the soil. We're looking mostly at the nutritional aspects of it. So it's important to do a textural test too, which we'll do together in the lab. Anybody have any other questions or concerns? We'll get deeper into the soil, like roots growing, on Wednesday. All right, well, we'll go ahead and sign off. Feel free to send me an email or give me a phone call if you have any other questions or concerns.